There's a star close to us, just 6 light years away, that has been a witness to the galaxy's oldest events. Barnard's star, one of the oldest stars in our cosmic neighborhood, is often overshadowed by its famous neighbors in the Alpha Centauri system. Yet, this dim red dwarf is a record holder. It is the closest single star to our Sun. For decades, astronomers have gazed at Barnard's star, speculating whether it harbored planets, only to have their theories repeatedly disproven. Until now, astronomers have finally confirmed a planet around Barnard's star, a sub-Earth exoplanet named Barnard B. With a mass about half that of Venus, Barnard B is one of the lowest mass exoplanets known, and one of the very few with a mass smaller than Earth. But in an era where we've cataloged over 5,000 exoplanets, why does the discovery of Barnard B still matter? What secrets could Barnard B hold about the formation of low-mass planets? Finally, and most importantly, could this discovery open a new chapter in our search for Earth-like worlds? Barnard's star holds a unique place in our cosmic neighborhood. While Proxima Centauri, part of the Alpha Centauri triple star system, is technically the nearest star, Barnard's star stands out as the closest single star to our solar system. This ancient star, estimated to be over twice the age of our Sun at about 10 billion years old, is notably smaller, cooler, and less luminous. Red dwarfs like Barnard's star are the most common stars in the universe. They are estimated to make up around 75% of fusing stars in our galaxy. They are known for their low mass, cooler temperatures, and exceptionally long lifespans that can extend to trillions of years. It's thought that no red dwarf has ever died in the universe so far. With only about 14% of the Sun's mass and a surface temperature of around 3,200 Kelvin, Barnard's star emits only a tiny amount of light, less than 0.04% of the Sun's brightness, making it impossible to see with the naked eye. But even though it's faint, there are 4 reasons why it is a great target for finding exoplanets. The first is its remarkable stability. Unlike many other red dwarfs, which often exhibit violent flares, Barnard's star remains relatively calm, reducing interference from stellar activity that could hinder the detection of orbiting planets. Secondly, its proximity to Earth makes it easier for astronomers to study and keep an eye on. Another interesting thing about Barnard's star is that it moves faster across the night sky than any other known star. Every 100 years, it appears to shift position by more than half the width of the Moon. This movement gives scientists an advantage, making it easier to detect small gravitational pulls from any planets that might be orbiting it. Finally, red dwarfs like Barnard's star often have planets that orbit very close to them. This close orbit makes it easier for astronomers to find planets, especially smaller, rocky ones, because their pull on the star is easier to detect. Together, these qualities have made Barnard's star a prime target for exoplanet exploration for over 55 years. From the early 1960s to the early 1970s, astronomer Peter Van de Kamp used astrometry to suggest that gas giants might be orbiting Barnard's star. Here's how it works. When a planet orbits a star, it doesn't just circle around the star directly. Instead, both the star and the planet move around a shared center of mass. The gravitational tug of a planet creates a subtle wobble, and by mapping this motion, astronomers can infer the presence of a planet around a star. However, detecting this tiny motion is complex and requires extremely sensitive instruments. Astrometry works best for giant planets closer to their stars, as their gravitational pull is stronger, and for stars relatively close to Earth. Over the years, scientists have ruled out the possibility of large gas giants orbiting Barnard's star. For example, a study in 2003 found no signs of close-in Neptune-like planets. And in 2013, another study confirmed that nothing bigger than Neptune could exist close to this star, which also ruled out planets in the star's habitable zone. Then, in 2018, a team led by Ignacy Ribas supported this conclusion. But they also made a surprising discovery. Using a different technique, called the radial velocity method, they found signs of a possible super-Earth orbiting Barnard's star. Radial velocity, also known as the Doppler method, is one of the most precise and widely used techniques for detecting exoplanets. Like astrometry, it looks for tiny wobbles in a star caused by a planet's gravity. But it works differently. Instead of directly measuring the star's position, the radial velocity method checks for small shifts in the star's light spectrum, providing insight into the presence and properties of potential planets. When a star moves slightly forward or away from Earth, its light changes because of the Doppler effect. When the star moves toward us, its light waves get compressed, which makes the light shift a bit toward the blue end of the spectrum. When it moves away, the light waves stretch out, shifting toward the red end of the spectrum. This subtle shift in color helps astronomers measure the star's motion, even though we can't actually see the planet itself. By tracking these color changes, scientists can detect the influence of an orbiting planet. This effect is similar to what you experience when an ambulance passes by. As it approaches, the siren sounds higher-pitched because the sound waves are compressed. As it moves away, the pitch drops due to the stretching of the waves. In the radial velocity method, the siren is light and the pitch change becomes a color shift in the star's spectrum. If a star's light shows a regular shift from blue to red, it suggests a repeating pattern likely caused by an orbiting planet. By measuring the strength and frequency of these shifts, astronomers can estimate the planet's mass, as well as the size and shape of its orbit. In 2018, this technique proved to be a turning point in the hunt for planets around Barnard's star. Now, let's shift from discovering planets to discovering opportunities, because the same principle applies to businesses. Just like astronomers need a clear way to track tiny shifts in starlight, entrepreneurs need a smart way to track leads, manage sales, and grow their business efficiently. That's where Odoo's CRM application comes in. With Odoo, every opportunity is neatly organized as a card with all the essential details at a glance. The Kanban view makes managing sales effortless. Just drag and drop deals as they move through the pipeline, giving you a clear picture of your revenue at each stage. Communication is just as effortless. With Odoo, you can quickly schedule calls, to-dos, and meetings while keeping all email exchanges in one place for easy access. Automated email templates and ChatGPT integration save time, making customer interactions smooth and efficient. Entrepreneurs can also track revenue forecasts, analyze team performance, and create custom dashboards to refine their strategy. The best thing is that you can use Odoo CRM app for free, as your first app is free for life, with a custom domain name free for 1 year. So, get your business organized today by clicking the link in the description. Now, back to space. In 2018, using a radial velocity method, researchers identified a possible planet in the Barnard system with a minimum mass of 3.3 Earth masses and an orbital period of 233 days. This discovery was especially exciting because it hinted at a potentially habitable planet near our solar system. However, the study faced challenges. The radial velocity method relies on small shifts in a star's spectrum. But these shifts can also be affected by the star's own activity. For example, star spots, cool dark patches on a star's surface, can change the star's light as they rotate into view and disappear. This can create a radial velocity signal that looks like it's from an orbiting planet, but is actually due to the star's rotation or its cycles. Other factors, like magnetic activity or temperature changes, can also produce false radial velocity signals. And this is exactly what happened in Barnard's star's case. In 2021, a study led by Lubin took a closer look at the 233-day signal reported in the 2018 study and questioned whether it really came from a planet. They found that this 233-day cycle matched closely with an actual pattern related to Barnard's star's rotation and magnetic activity. This suggested that the signal might not be from a planet at all, but rather from the star's own behavior. This argument gained more support from a 2022 study. Researchers used an instrument that measures the radial velocity of stars in the infrared spectrum. Observing in infrared light can sometimes lessen the effects of a star's activity, making it easier to tell apart signals caused by planets from those caused by the star itself. This study further suggested that the original 233-day signal was likely not from a planet, but rather from Barnard's star's own behavior. As a result, the question of whether planets orbited Barnard's star remained unanswered, keeping the mystery alive. Just as the mystery around Barnard's star seemed to grow, a new study came out in October 2024 with fresh data and new techniques. Led by Gonzalez Hernandez, this study used an advanced instrument called the espresso spectrograph, which is designed to detect very tiny movements in stars caused by orbiting planets. Installed on the Very Large Telescope, espresso can measure these movements with incredible accuracy, down to 10 centimeters per second. This study observed Barnard's star 156 times over 4 years, from May 2019 till July 2023, to look for signals that might reveal Earth-like planets around it. By carefully analyzing the data, the team aimed to separate any true planetary signals from background noise caused by the star's own behavior. Now here's the interesting part. Although they didn't find evidence to support the 233-day planet candidate from 2018, they found 4 strong signals, each with periods under 10 days. The most notable was a signal with a period of 3.15 days, which was extremely significant, with less than a 0.1% chance of being a false alarm. When they analyzed this signal further, they estimated that if it's from a planet, the planet would have a minimum mass of about 0.37 times Earth's mass, or about 3 times the mass of Mars. This planet would have a nearly circular orbit very close to the star, at a distance of just 0.0229 AU, which places it out of Barnard's star's habitable zone. The small size and close orbit of this planet suggests it is likely a rocky world. However, its extreme conditions make it far from Earth-like or habitable. Its equilibrium temperature is estimated to be about 400 Kelvin, assuming an albedo of 0.3. Albedo is an important factor for understanding a planet's temperature. It measures how much incoming light from the star is reflected back into space rather than absorbed. An albedo ranges from 0 to 1. A higher albedo means the planet reflects more light. A lower albedo means more energy is taken in, raising surface or atmospheric temperatures. So Barnard B's relatively high temperature is partly due to its low albedo and close distance to Barnard's star. For Barnard B, researchers use albedo of 0.3 as a baseline. This is a moderate value commonly applied to rocky planets with thin atmospheres similar to Earth's, which also has an albedo of about 0.3. While Barnard's star is much cooler than our Sun, the planet's close orbit means it still receives enough heat for its estimated equilibrium temperature to reach a scorching 400 Kelvin. This is far above the range needed to support liquid water, reinforcing the idea that Barnard B is not a hospitable world. Alongside the confirmed signal, the researchers found 3 additional candidate signals with periods of 4.12 days, 2.34 days, and 6.74 days. These signals suggest possible planets with minimum masses of 0.31, 0.22, and 0.17 times the mass of Earth, respectively. If these candidates are real, they would also be in regions close to Barnard's star, where they'd receive much more radiation than Earth, likely making them too hot for Earth-like conditions. While more observations are needed to confirm these 3 additional candidates, The discovery of the 3.15-day planet is an exciting step forward. It shows that even low-mass, close-orbiting planets can be detected around a faint, nearby star like Barnard's star, adding valuable knowledge about its potential planetary system. The development of new, advanced telescopes like the Extremely Large Telescope or ELT and the James Webb Space Telescope is set to revolutionize how we study planets beyond our solar system. The ELT, with its massive 39-meter mirror, will be one of the most powerful optical telescopes ever built. It will allow astronomers to detect smaller, more distant exoplanets and study their atmospheres in detail, revealing information about their composition, climate, and even their potential to support life. Webb is already transforming exoplanet research with its incredible ability to observe in the infrared spectrum. This allows it to analyze the atmospheres of planets like Barnard B, detecting key molecules and providing insights into their surface conditions and atmospheric behavior. Together, the ELT and JWST will work hand in hand, offering deeper and more detailed explorations of distant worlds. So thank you for watching, and check out the link in the description to start your journey with Odoo today.